So this webinar sheds light on low-cost environmental sensing to deliver ground-based data from some of the most remote locations, which in our case are some desert areas around the Mediterranean. And on the right, you can see the link and the web, a snapshot of the web page to host the whole webinar series. So, having a quick look at the agenda, first our project manager will explain what CiROCCO is, and then a researcher from Cyprus will elaborate on our technological developments.
So good morning from my side as well, and welcome to fourth CiROCCO webinar. My name is Christoulova Athanasiou. I'm a senior project manager at the Institute of Communication and Computer Systems. ICCS is the coordinator of CiROCCO, and I'm the day-to-day project manager of this project. So before presenting you CiROCCO in a nutshell, I would like to express my special thanks to NOAA team, Eleni Athanasopoulou, Thanasis Koukoulis and University of Cyprus, and it's Petros Moussouridis standing there for organizing this webinar. Also, IBOS, Kleanthis Rotokritou for sharing with us the experience and the knowledge gained during all this period, and also previous experience related to the domain of deploying low-cost sensing nodes. And of course, special thanks to all attendees for taking the time to join us today. Great. So about some facts and figures about the project. The vision of the project is to establish an integrated sensing system. It is composed of a distributed network of low-cost sensing nodes combined with some higher-end sensing solutions, coupled with state-of-the-art data fusion, remote sensing, and simulation modeling techniques. Our network of sensors aims to enhance the current lack of ground observations in desert areas, since this is the main study areas of our project, offering an operational at the same time easy to maintain and expand solution. We foresee some commercialization services to be implemented during the course of the project, and in parallel, we foresee fair management of data and support cross-Copernicus ecosystem integration and simulation services. To implement this project, we have 12 partners joining forces coming from 7 different countries. As I said before, ICCS is the coordinator of the project. So we have 5 academic and RTOs joining forces. Apart from ICCS, we have National Observatory of Athens, CEDARE, which is our local partner in Egypt, University of Cyprus, and CICIC, our local partner in Spain. 3 SMEs, IBOS from Cyprus, ASTROCAS from Switzerland, and Innocence from Serbia. 1 industrial partner, Intra, which is a net company located in Athens, in Greece, and 3 public organizations, Demos, a municipality in Cyprus, Ministry of Labor, again in Cyprus, and Visium, a local partner in Serbia. 3 years duration and approximate EU funded 4 million. So the main objectives of CiROCCO, main business objective has to do with the installation and operation of in-situ low-cost standalone electronic sensing nodes, and we aim to have our local communities involved in the whole process of exploiting our nodes. Technical objective has to do with the establishment of a low-cost and sustainable network of these nodes that monitor the conditions in undersampled desert areas and ecosystems. Another technical objective, development of data processing services based upon ICT infrastructure, and also improvement of the quality of our services using data fusion services. Scientific and innovation objective has to do with the enhancement of climate change models and supporting the research of the European Green Deal challenges. Another scientific innovation objective has to do with cross-Copernicus ecosystem integration and assimilation, and an impact maximization objective has to do with the adoption of CiROCCO solutions, tools and services by the wider community, so to ensure that eventually the project will have a significant impact. In terms of the concept, here you can see an overview of what CiROCCO does in our picture. So we have a mix of low and higher cost sensing nodes, in situ nodes that are combined with data sets from EO datasets. So we foresee data fusion between Earth observation and in situ measurements, a mixture of low cost and high-end sensing solutions. This communication takes place through wireless and satellite communication channels for collecting datasets. And in the end, all the datasets provide, all these sensors provide datasets, to serve the needs of 4 different services that are foreseen in the project. First one is air quality early warning system for human health. The second one, renewable energy systems planning. Land use and ecosystem management is the third one. And the fourth service we foresee is modeling of greenhouse gases and particles emission. Here you can see some pictures of the nodes that are going to be installed. Some of them are already installed in our pilots. So we have in total 9 higher quality mid-coast stations, these AQMS sensors. We have some portable devices, 6 AOD devices, which are sun photometers. And in total, by the end of the project, we will have installed 60 low-cost sensing nodes. Custom-made nodes, I will not go into detail because this is what Kleanthis will present us in a while. So the main outcomes, sensors will be installed in 3 desert regions and apart from their installation in the municipality in Cyprus, fully operational for 10 months, covering an area expanding over 2,000 square kilometers, 69 stations in total, 10 parameters. Actually, that was our the KPI was to reach 10 parameters. We are beyond that. A target was to make available our local sensing system with 60% lower price than the current market. Validation of datasets through the application in our 4 services, as I mentioned before, and offering increased accuracy in the developed models and improvement by 10% with including in-situ datasets and collaboration with at least 5 working groups of GEO, Copernicus and ESA. And here you can see an overview of our 4 pilots, and I will not go into detail to that, just to show you the geographic distribution of them. Our first pilot is in Egypt, in Benban Solar Farm, and this pilot has to do with renewable energy systems planning. Our second pilot is in Cyprus, desert dust storm events monitoring. The third pilot is in Serbia, Deliblato Sands in Serbia, and has to do with sustainable environmental restoration support. And the fourth pilot is in Spain, in the Tabernas Desert, and the main purpose of this pilot has to do with the modeling of greenhouse gases and particles emission. So that was in very brief what we aim to do and what we have started doing in this project. I will stop sharing and I will give the floor to Eleni or directly to Kleanthis for the next presentation.
Thank you, Chrysoula. Please keep your questions after Kleanthis' insights on the monitoring system of CiROCCO, and Kleanthis, you can share your screen.
Sure. Just a minute to share my screen. Hello, everyone. Thanks a lot for organizing this webinar, Eleni. So as introduced by Chrysoula, who is the project coordinator, I'll walk you through the design and development of the low-cost sensing nodes, or as we call them in the project, LCSN. So these devices, they are forming the backbone of the CiROCCO project in terms of the environmental monitoring networking. So a brief overview of these devices, they are field-ready autonomous systems that are engineered to capture a high-resolution environmental data across the Mediterranean and desert pilot sites. I will focus on how we have moved from the initial prototype to a fully deployable platform, the lessons we learned, and the measurable impact across these devices. So when we started designing these nodes, our aim was to achieve something that can survive the 45 degrees centigrade that can be achieved in Egypt, and also still deliver reliable data every single day, while at the same time survive the extreme low winter temperatures experienced in Serbia. So this environmental range has defined our entire design philosophy. We'll begin by understanding the environmental monitoring gap the CiROCCO is trying to address. So the challenge faced is that in desert and semi-arid regions, among the least, they are among the least instrumented and continuously observed areas on Earth. Satellite models depend on continuous ground calibration data, which remains scarce in these regions. And with CiROCCO, we aim to bridge this gap through a network of autonomous, low-cost, and easily maintainable sensing nodes. This lack of data limits our ability to accurately model air quality and dust transport, and that's exactly what CiROCCO is set out to change. So by taking in Cyprus and Egypt as examples, dust events can occur overnight on satellite images, but without any ground calibration data, we cannot really verify that these events, how intense they are. So in reality, we're working to make the change of that, and we will see now how these challenges mentioned have shaped our design evolution. So the vision of the CiROCCO is to, well, sorry about that. So here we're going from the research prototype to a field-ready network. As you can see on the image here, we have two devices: the low-cost sensing node version 1 and low-cost sense version 2. The first version was designed as a functional prototype that was validating sensing accuracy and overall architecture. It has used a box-in-a-box approach. What that means in simpler terms is that it had an inner sealed chamber, which was housed inside an external shell. So this enclosure kept the temperature within certain limits, but this has introduced extra thermal complexities that required higher maintenance effort and additional costs. So we have moved forward with the second version, which we have removed the inner enclosure, and we are improving the airflow and the heat dissipation. And by replacing one major sensor, that is the low-cost sensor, which is measuring the optical particles, we have achieved a better tolerance of higher temperature, and that enabled this design. Additionally, this design has allowed us to reduce the size. So in the first version, we were in 40 centimeters height by 20 centimeters. Now we have shrunk it down to 30 by 25 at 15 centimeters. So internally, the second version is introducing modular PCBs, which are for power, digital, and sensor integration, and has refined the cabling for quicker servicing. So this compact form factor and modular electronics are making this device maintenance faster and easier. So getting into the internal components that are available in each device, as mentioned previously, we have by Chrysula, we are having various sensors that are ensuring high quality, and they are used for meteorological. For example, we have temperature, humidity, pressure, wind, and the solar radiation. Then we have soil moisture temperature. And as atmospheric parameters, we have optical particle counter and carbon dioxide. These sensors are shown here just for a reference of what is their size. And each device follows a 3-board modular design. We begin with the power PCB, which is managing the solar input, the battery charging, and the overall power of all the subsystems. Then we have a digital PCB, which is handling the control and the data transfer. And finally, a sensor integration board, which is offering plug-and-play connections to the various sensors. Version 1 and version 1 to version 2 major improvements have mentioned previously. What wasn't mentioned before is that for connectivity options, we include LoRa, which is for a long-range transmission that uses low power. Then we have the LTE that uses the telecommunication bands. Then we have Wi-Fi, and finally we have a satellite option as a backup for remote sites. Here I will try to showcase how it's the transfer of the data from the sensors goes. So we have the devices who are measuring data by the sensors. The sensors are sending the information to the main control unit. Then the main control unit is using a communication module. Depending on the situation, it's going to be either Wi-Fi, LTE, or LoRa. And then from there, we'll go to the CiROCCO cloud. And from there, each pilot can visualize the data for further analysis. So for communication protocols, we have used MQTT over the TLS, which allow us for a secure real-time data transfer. And each data packet includes a time of the acquisition of the data and a unique device ID that allows for full traceability in case needed in the analysis. Finally, this architecture allows for energy optimization by using adaptive reporting intervals and allow the device to go into an ultra-low power sleep mode, as we call it, which extends the battery autonomy of the system. And it can this can be translated that in these remote desert areas, we can get the data securely and with full traceability anytime needed. So as a result, this connectivity backbone transforms each node from a sensor box into a live network observatory. Here I'm showing the different ways the communication is transferred from the local sensing nodes to the cloud infrastructure that has been developed by Net Company. On the top side, we have the LoRa mesh network that goes to a gateway device that uses telecommunication networks. And then from there goes to the cloud infrastructure. And an alternative communication is using Wi-Fi. So from the devices goes using Wi-Fi to the internet, and from there to the Net Company Stream 100 platform. So how do these engineering upgrades are translating into real impact? I have tried to summarize this into 4 categories. So first of all, we have the significant reduction in the maintenance cost due to the reliability of this system. They are scalable, so that translates to easier assembly and field deployment thanks to the simplified housing and the overall design. They are standardized data enables cross-region analysis, and they are durable. For example, in Cyprus, we have one unit that has been running continuously for over 6 months now with close to zero maintenance. That kind of stability is what allows us to think of the system not as prototypes, but as operational tools. And it's a step towards operational maturity of the long-term environmental observations. So with these results in hand, our next focus is to scaling up and putting these low-cost sensing nodes into the full pilot operations. And as a result, what's coming next is within CiROCCO project and with the upcoming low-cost sensing node version 2 deployment, our focus is shifted now towards the pilot scale testing and the broader integration activities, including the large-scale pilot expansion and continuous calibration campaigns, and any potential open hardware release to enable replication by research centers beyond CiROCCO. So as we scale up, we're inviting research partners to co-deploy and test these new solutions that will allow to extend the CiROCCO research beyond our current pilots. And finishing up, our goal is not only to measure this information, is to make this invisible dust particles measurable continuously and affordable. So with that in mind, thanks a lot for your attention, and I will be happy to take any questions you may have.